201 students. Welcome to Module 2 of our Chemistry Lecture course. In this lecture video, we will discuss Module 2.1 entitled Water as Universal Solvent, particularly the properties of water molecule that makes it a great solvent along with the properties of aqueous solutions. After this lecture, you must be able to determine and describe the types of intermolecular forces between atoms and molecules in liquid phases, such as ion-dipole attraction and hydrogen bonding. You must be able to define solute and solvent in aqueous solutions. And lastly, you must be able to describe the fundamental properties of solutions. Mixture is a combination of two or more substances that do not combine chemically but remain the same individual substances. And these substances can be separated by physical means. There are two types of mixture, namely heterogeneous and homogeneous mixtures. Hetero comes from the Greek word heteros, which means different, and homos comes from the Greek word homos, meaning the same. Heterogeneous mixtures can be segregated into separate parts that you can visibly see the individual components. Classic examples are rocks, wherein they are made up of different and distinct fragments of minerals, while homogeneous mixtures are so well mixed that you cannot see the separate components in the mixture. Example of homogeneous mixture is seawater, where the salt completely dissolves in water and are evenly mixed that you cannot see the salt and water particles anymore. Homogeneous mixtures are also called as solutions. Solutions are defined as homogeneous mixtures that are mixed so thoroughly that neither component can be observed independently of the other. As mentioned, these components or substances can be physically separated. Now, if salt water is considered as a solution, how can it be physically separated? 1. You can evaporate the water to be left with the salt as solid. Or 2. If you want to collect the water, you can use distillation process. The major component of a solution is called the solvent, while the minor component or components are called solute. Solutes are the substances being dissolved, while the solvent is the substance that dissolves the solute. So say if you are enjoying an iced tea drink while watching this lecture video, what you are drinking is an example of solution, composed of water as the solvent and the iced tea mix as the solute. In addition to a solution made by adding a solid to a liquid, a gas can also be a solution. For example, the air we breathe is a solution in which nitrogen is the solvent and oxygen and other gases are the solute. Metals, like brass, can be a solution of solids in solids. Brass is an alloy of the solute zinc in the solvent copper. The solute and solvent can either be a solid, liquid, or gas in a solution. We now move on to a common type of solution, which is the aqueous solutions. Aqueous solutions are solutions in which water is the solvent. Water is a great solvent. It is also called as the universal solvent. Our body has a lot of water for good reason. A lot of biological compounds dissolve in water. So water is more of a personal solvent. Ocean water is of course a solution. It is not a pure water. It is water with a lot of salts dissolved in it. This deliciously looking glass of beer contains water, which accounts up to 95% of its content, with malted barley and yeast as its solute. And of course, in a chemistry laboratory, water is an extremely important solvent. Lots of so-called polar compounds dissolve in water. Why is water such a great solvent? Let's have a closer look at the water molecule. It has an oxygen and two hydrogen atoms, thus H2O is its molecular formula. The hydrogen atom has a little bit less electron density than the oxygen atom. What does this mean? Some of the electron of the oxygen will partner with an electron from the hydrogen to form a covalent bond. However, if you look carefully at this, we notice that the electrons that form this bond tend to spend a little bit more time on the oxygen side than on the hydrogen side. Even though the electrons are shared, it seems that they are not shared equally. The oxygen atom is more electronegative, which means it tends to attract electrons a little more than the hydrogen does. And it doesn't mean that there is an actual charge there. The delta minus indicates that there is a partial negative charge on the oxygen, while the delta plus in the hydrogen indicates a partial positive charge on the hydrogen. What does this mean? It means that this molecule has a polarity. There will be a different kind of Coulombic interaction with different molecules. Many of the properties of water follow from this phenomenon called polarity. Hydrogen bond is a very special type of dipole-dipole interaction. It is a very strong type of dipole-dipole attraction force. Hydrogen bonds occur whenever it is directly attached to nitrogen, oxygen, or fluorine. Hydrogen from one molecule can associate itself with the negative end of the dipole of another. Why are hydrogen bonds a lot stronger than dipole-dipole, even though they work the same way? 1. The electronegativity difference is higher between hydrogen and nitrogen, oxygen, or fluorine. Thus, they are highly polarized. And 2. The hydrogen atoms are very small, that results to higher force of attraction. Because of the hydrogen bonding between water molecules, water has high specific heat, high boiling point, and higher density with it the bond between hydrogen and oxygen within a single water molecule is not a hydrogen bond. That is a covalent bond, and it is an intramolecular force that brings the hydrogen and oxygen atoms together. The hydrogen bonds exist between molecules. It is an intermolecular force. Inter means between, and intra means within. The oxygen atom of water carries a partial negative charge, and the hydrogen atoms are partially positive. So water molecules may be attracted to each other. The oxygen of one water molecule is attracted to the hydrogen of another. So that is the hydrogen bond within water. In total, one water molecule can participate in 4 hydrogen bonds with other molecules. The interaction between a cation or an ion with water is called an ion dipole. As discussed, water is a polar molecule. In fact, it is a permanent dipole, which is a molecule that is always polar. So the oxygen atom that has a partial negative charge will be attracted to cations, and the hydrogen atom from water will be attracted to anions. This electrostatic interaction is called ion-dipole interaction. So if you want to dissolve sodium chloride in water, the sodium will be surrounded by water molecules, with oxygen atom, being a partial negative, will be attracted to the positive charge of the sodium cation, while the hydrogen atom will be attracted to the negative charge of the chlorine ion. So that's how you dissolve ionic solutes in water. The next type of intermolecular force in water is dipole-dipole interaction, which occurs between two polar covalent molecules, wherein the partial positive atoms of one molecule is attracted to the partial negative atoms of another. Hydrogen bond is a special type of this intermolecular force. For non-ionic solute, if the compound is polar, like water, the solubility will be high in water. If the compound is non-polar, like fat or oil, the solubility in water will be low.
If we have a water solution with no ions in it, and you put a current through the water solution, the bulb will remain unlit because the electrons and the charges will not go through the water. And if we put some salt in it, we actually create pluses and minuses in the water, which are charge carriers in the water, and now the lamp will be vaguely dim but will be turned on. If we add more and more salt, which will generate more charge carriers, we can actually form a current between these two electrodes to the water. And now it is conducting. This is one way to classify aqueous solutions that are ionic. Solutions with high concentration of dissolved ions are strong electrolytes, and vice versa, solutions with low concentrations of dissolved ions are weak electrolytes. Strong electrolytes will conduct current and include soluble salts, strong acids, and strong bases. These strong electrolytes will be fully dissociated into ions when in water, while weak electrolytes include weak acids and weak bases. When dissolved in water, a weak acid only partially dissociates into H plus ions and anions, while a weak base only partially generates OH minus ions and cations. In addition, there are compounds that are called non-electrolytes like sugar. Non-electrolytes produce no ions when dissolved in water and form non-ionic solutions. The maximum amount of a substance that can be dissolved in a given volume of a solvent at a given temperature and pressure is called solubility. Solubility depends on the polarity of the solute and solvent, as discussed from the previous sections, and the temperature of the solvent. A solution that has not reached its maximum solubility is called an unsaturated solution. This means that more solute can still be added to the solvent and dissolving would still occur. A solution that has reached its maximum solubility is called a saturated solution. If more solute is added at this point, it will not dissolve into the solution. Instead, it will remain precipitated as a solid at the bottom of the solution. Supersaturated solutions are solutions that have dissolved solute beyond the normal saturation point. When considering the solubility of solids, the relationship of temperature and solubility is not simple or predictable. Although, the solubility of a solid generally increases with increasing temperature. There is no simple relationship between the structure of a substance and the temperature dependence of its solubility. The variation of solubility with temperature has been measured for a wide range of compounds, and the results are published in many standard reference books. The solubility of gases in liquids is much more predictable. The solubility of gases in liquids decreases with increasing temperature. This is the end of the lecture for Module 2.1. Please watch out for our next lecture video where we will discuss how to quantify solutions, particularly expressing concentrations of these solutions. Should you have questions and clarifications regarding the lecture, please post it in the discussion board of your respective Blackboard course sites.